There is a result in theoretical physics from 2019 that I think is one of the most important and least understood developments in the foundations of physics in the last 20 years. It does not involve a telescope or a particle accelerator. It does not involve a new experiment or a new observation. It involves a calculation, a specific mathematical derivation carried out by a group of theoretical physicists that produced an answer that should have been impossible, an answer that required information to escape from inside a black hole, an answer that, if correct, resolves one of the deepest paradoxes in the history of science, and an answer that tells us something about the structure of space-time itself that we are still working to fully understand. I want to take you through this story carefully because it is both technically intricate and conceptually profound, and because I think most popular accounts of it either simplify it to the point of distortion or obscure it in technical jargon that makes it inaccessible. The story connects quantum mechanics and general relativity at their most fundamental levels, involves black holes and the nature of space-time and the meaning of information, and arrives at a conclusion that changes what we think we know about the interior of a black hole and about the relationship between quantum mechanics and gravity. Let me start at the beginning with the paradox that the 2019 result was attempting to resolve. Let me start at the beginning with the paradox that the 2019 result was attempting to resolve. But before the paradox, there is a discovery that made the paradox possible, and I think it deserves its own careful treatment because it is one of the most remarkable insights in the history of physics. In the early 1970s, Jacob Bekenstein was a graduate student working with John Wheeler at Princeton. He was thinking about a puzzle that the second law of thermodynamics seemed to pose for black holes. The second law says that the total entropy of an isolated system never decreases, but black holes seem to violate this. If you drop a hot cup of tea into a black hole, the entropy of the tea, the disorder associated with the random motion of its molecules, disappears behind the event horizon. From the perspective of the outside universe, the entropy is simply gone. The total entropy of everything outside the black hole has decreased. The second law seems to be violated. Bekenstein's solution was elegant and radical. He proposed that black holes themselves carry entropy, and that this entropy is proportional to the area of the event horizon. The second law, properly stated, applies to the total entropy of all matter plus the entropy of black holes, and this generalized entropy never decreases. When you drop the hot tea into the black hole, the horizon area increases by exactly enough to compensate for the lost entropy of the tea. The formula for black hole entropy is remarkably simple. S equals K times A divided by 4 times the Planck length squared, where K is Boltzmann's constant. A is the area of the horizon, and the Planck length is approximately 10 to the minus 35 meters. The factor of 1/4 and the Planck length are not arbitrary. They are set by the constants of nature in a way that makes the formula dimensionally consistent and connects it to quantum gravity. When Hawking derived his radiation formula in 1975, he confirmed Bekenstein's entropy formula from a completely different direction. The temperature of Hawking radiation, combined with the thermodynamic definition of temperature as the derivative of energy with respect to entropy, gives exactly Bekenstein's formula for the black hole entropy. The two independent calculations agreed perfectly. Black holes are thermodynamic objects. They have temperature, they have entropy, they obey the laws of thermodynamics. But this agreement, satisfying as it was, immediately raised the information paradox. The entropy of a system is a measure of the information we do not have about its microscopic state. High entropy means we know little about the specific microstate. If the black hole has enormous entropy, it has enormous microscopic structure that we cannot observe from outside. Where is this microstate information stored? And what happens to it when the black hole evaporates? The black hole information paradox was formulated by Stephen Hawking in 1975. In that year, Hawking published a landmark paper in which he showed that black holes are not completely black. They emit radiation. The mechanism is quantum mechanical. Near the event horizon of a black hole, the extreme curvature of space-time causes quantum vacuum fluctuations to produce pairs of particles, one of which falls into the black hole and one of which escapes to infinity as radiation. The escaping radiation carries energy away from the black hole, causing it to slowly lose mass and eventually, over an incomprehensibly long time, to evaporate completely. This was a profound discovery. Before Hawking's calculation, black holes were understood to be purely absorbing objects. Once something crossed the event horizon, it was gone forever. Nothing could escape. Hawking showed that this was not quite right. Something does escape. Thermal radiation, now called Hawking radiation, with a temperature inversely proportional to the mass of the black hole. But Hawking's calculation contained a deeply disturbing feature. The radiation he calculated was exactly thermal. It was a perfect black body spectrum, the same kind of radiation emitted by a hot oven or a glowing ember, characterized entirely by a single temperature and containing no information about what fell into the black hole. An old physics textbook that fell into the black hole and a cloud of hydrogen gas that fell into the black hole would produce identical Hawking radiation according to Hawking's calculation. The specific information encoded in the textbook, everything that made it a textbook rather than a cloud of gas, was nowhere in the radiation. This was a profound discovery. Before Hawking's calculation, black holes were understood to be purely absorbing objects. Once something crossed the event horizon, it was gone forever. Nothing could escape. Hawking showed that this was not quite right. Something does escape. Thermal radiation, now called Hawking radiation, with a temperature inversely proportional to the mass of the black hole. Let me describe the physics of Hawking radiation in more detail, because understanding what makes it thermal is essential for understanding why it creates a paradox. The mechanism that Hawking identified involves the quantum vacuum near the event horizon. In quantum field theory, the vacuum is not empty. It is full of quantum fluctuations, virtual particle-antiparticle pairs that pop into existence and annihilate almost immediately, borrowing energy from the vacuum for the brief duration of their existence. This is the same quantum vacuum I described in the video about why empty space cannot be empty. Near the event horizon of a black hole, something special happens to these virtual pairs. The extreme space-time curvature at the horizon means that a virtual pair that forms right at the horizon can be split. One particle falls inside the horizon while the other escapes to infinity. The particle that escapes cannot annihilate with its partner because the partner is now inside the horizon and cannot come out. The escaped particle becomes real. Its partner, falling into the black hole, carries negative energy that reduces the mass of the black hole slightly. The black hole loses mass, and the escaped particle appears as radiation at infinity. The temperature of this radiation, the Hawking temperature, is given by a remarkably simple formula. T equals the reduced Planck constant times the speed of light cubed divided by 8 pi times Newton's gravitational constant times the mass of the black hole times Boltzmann's constant. The key feature is that the temperature is inversely proportional to the mass. A solar mass black hole has a Hawking temperature of about 10 to the minus 8 Kelvin, far colder than the cosmic microwave background. A black hole would need to be extremely small, about 10 trillion times lighter than the sun, to have a Hawking temperature comparable to room temperature. Because the Hawking temperature is so low for astrophysical black holes, the Hawking radiation is completely negligible compared to the radiation absorbed from the cosmic microwave background. Astrophysical black holes are not evaporating, they are accreting. But in principle and over cosmological timescales, the Hawking process will eventually dominate and the black hole will evaporate. The crucial feature of the Hawking radiation, the feature that creates the paradox, is that it is exactly thermal. The spectrum of the radiation is precisely a blackbody spectrum at the Hawking temperature. A blackbody spectrum is the maximum entropy spectrum for a given energy. It is the least informative spectrum possible. It contains no information beyond the temperature itself. Two different black holes of the same mass would produce identical Hawking radiation spectra regardless of what they were made of or what had fallen into them. But this calculation involves an approximation that proved to be crucially important. The calculation is semi-classical. It treats the quantum fields near the black hole quantum mechanically, but treats the space-time geometry of the black hole classically, ignoring quantum gravitational effects on the geometry itself. This approximation is excellent for large black holes, where the quantum gravitational corrections to the geometry are tiny, but it completely misses any information encoding correlations that might be present in the quantum gravity corrections to the radiation. The paradox arises because if the radiation is exactly thermal, and if the black hole eventually evaporates completely, the information is nowhere. It is not in the radiation, which is thermal and featureless. It is not in the black hole, which no longer exists. It has simply vanished from the universe. If the Hawking radiation contains no information, and if the black hole eventually evaporates completely, then the information that fell into the black hole has been permanently destroyed. The quantum state of the matter that formed the black hole and the quantum state of everything that subsequently fell into it has been converted into the quantum state of the Hawking radiation, which is purely thermal, which carries no information about the infalling matter. This is catastrophic for quantum mechanics. The fundamental law of quantum mechanics says that the evolution of a quantum state is unitary. Unitary evolution is reversible. If you know the current quantum state of a system and the equations governing its evolution, you can calculate the quantum state at any earlier time as well as any later time. No information is lost. The past is completely encoded in the present. Information destruction by black hole evaporation would violate this unitarity. It would mean that quantum mechanics was not a complete description of nature, that there was a physical process, black hole evaporation, in which information was genuinely and irreversibly destroyed. The quantum state of the infalling matter would simply cease to exist when the black hole finished evaporating, leaving behind only the featureless thermal radiation. Hawking believed this was actually the case. He argued for decades that black hole evaporation did destroy information, that quantum gravity required a modification of quantum mechanics that allowed non-unitary evolution. His position was that the information was truly lost, not hidden somewhere waiting to be recovered, but genuinely, permanently gone. Most physicists who thought carefully about the problem were uncomfortable with this conclusion. John Preskill, the Caltech physicist, was so uncomfortable that in 1997 he made a formal bet with Hawking. Preskill bet that information would be found to be preserved in black hole evaporation, that the Hawking radiation would be found to carry the information, however scrambled, however difficult to extract, that fell into the black hole. The prize was an encyclopedia of the winner's choice, because an encyclopedia contains a lot of information. Most physicists who thought carefully about the problem were uncomfortable with this conclusion. John Preskill, the Caltech physicist, was so uncomfortable that in 1997 he made a formal bet with Hawking. Preskill bet that information would be found to be preserved in black hole evaporation, that the Hawking radiation would be found to carry the information, however scrambled, however difficult to extract, that fell into the black hole. The prize was an encyclopedia of the winner's choice, because an encyclopedia contains a lot of information. Kip Thorne sided with Hawking. The three of them signed a formal bet document, the kind of lighthearted but serious tradition in theoretical physics that Hawking enjoyed. The terms were specific. Hawking and Thorne bet that information swallowed by a black hole was permanently lost to our universe. Preskill bet that it was not. The bet was not resolved quickly. For years, neither side could prove their position. The problem was that the calculation Hawking had done was a semi-classical calculation. It treated the quantum fields near the black hole quantum mechanically, but treated the space-time geometry classically. This approximation is excellent for large black holes, but might break down as the black hole gets small near the end of its evaporation. Perhaps the information was encoded in the quantum gravitational corrections that the semi-classical calculation missed. But this explanation faced a serious difficulty. The quantum gravitational corrections to any individual quantum of Hawking radiation are expected to be tiny for large black holes. For the information to be preserved, the corrections would need to be correlated across many quanta in a highly specific way, creating entanglement between early and late Hawking radiation that seemed impossible to produce through any local physical mechanism near the horizon. Then in 2004, at a conference in Dublin, Hawking gave a talk that surprised the community. He announced that he had changed his mind. He conceded the bet to Preskill. He had convinced himself, through an argument based on ADSES, CFT, that information was indeed preserved in black hole evaporation, that the black hole must eventually return all the information it absorbed. He gave Preskill a copy of Total Baseball, the Encyclopedia of Baseball Statistics, as his forfeit. Thorne did not concede. He felt the argument was not conclusive. And he had a point. Hawking's 2004 argument was intuitive rather than rigorous. It relied on the AD-CFT correspondence, which provides strong evidence that information is preserved but does not provide the specific mechanism. The precise way in which the information escapes from the black hole remained mysterious. The concession was more a change of intuition than a change based on a definitive calculation. The definitive calculation came in 2019. The bet was not resolved quickly. For years, neither side could prove their position. It treated the quantum fields near the black hole quantum mechanically, but treated the space-time geometry of the black hole classically. This is a good approximation for large black holes at early times, but it might break down as the black hole evaporates and becomes small, where quantum gravitational effects become important. Perhaps the information was encoded in the quantum gravitational corrections to the Hawking radiation that the semi-classical calculation missed. But this explanation faced a serious difficulty. The quantum gravitational corrections to the Hawking radiation are expected to be tiny for large black holes. Each individual quantum of Hawking radiation would need to carry only an infinitesimal amount of information for the total information to be preserved. This seemed to require a kind of non-local correlation between early and late Hawking radiation quanta that was very difficult to understand from the perspective of local quantum field theory. How could a photon emitted near the end of the black hole's evaporation know about a photon emitted near the beginning when the two events are separated by an astronomical time and when the early photon is by now dispersed across the universe? This difficulty was sharpened into a specific argument called the firewall paradox, published in 2012 by Ahmed Almheiri, Donald Marolf, Joseph Polchinski, and James Sully, known collectively as AMPS. The AMPS argument showed that information preservation, unitarity, and the smoothness of the event horizon for an infalling observer cannot all be simultaneously true within the framework of local quantum field theory. If information is preserved in the Hawking radiation, and if the early and late Hawking radiation are quantum mechanically entangled in the way required for information preservation, then the event horizon cannot be smooth for an infalling observer. There must be a firewall at the horizon, a wall of high energy radiation that destroys anything that tries to cross it. The firewall paradox was deeply disturbing because it challenged one of the most fundamental predictions of general relativity. General relativity says that the event horizon of a black hole is not a special place for an infalling observer. An observer falling through the horizon of a sufficiently large black hole would notice nothing special at the moment of crossing. The horizon is not a physical surface. It is simply the boundary of the region from which escape is impossible. An infalling observer's local physics should look exactly like flat space-time physics as they cross the horizon. This is the equivalence principle applied to black holes, and it is one of the most basic and well-tested principles of general relativity. The firewall paradox said that either information is destroyed, violating quantum mechanics, or the horizon is not smooth, violating the equivalence principle. One of the two most fundamental theories in physics had to be wrong. Which one? The firewall paradox was deeply disturbing because it challenged one of the most fundamental predictions of general relativity. General relativity says that the event horizon of a black hole is not a special place for an infalling observer. An observer falling through the horizon of a sufficiently large black hole would notice nothing special at the moment of crossing. The horizon is not a physical surface. It is simply the boundary of the region from which escape is impossible. An infalling observer's local physics should look exactly like flat space-time physics as they cross the horizon. This is the equivalence principle applied to black holes, and it is one of the most basic and well-tested principles of general relativity. Let me be more specific about the AMPS argument, because I think it is important to understand why the paradox is so sharp and why it forced the community to take seriously that something fundamental had to change. The argument involves three principles that seem individually unassailable but are collectively contradictory. The first principle is unitarity. Quantum mechanics is unitary. Information is not destroyed. The quantum state of the universe evolves in a reversible way. This principle is so fundamental that abandoning it would require a complete revision of quantum mechanics. The second principle is effective field theory outside the horizon. The physics of quantum fields in the region outside the black hole horizon should be described by ordinary quantum field theory in curved spacetime, at least for observers who stay outside the horizon. This is the framework that gives us Hawking's original calculation, and that is confirmed by many other calculations. The third principle is the no-drama condition. An infalling observer crossing the event horizon of a large black hole should not experience anything dramatic. This is the principle from general relativity I just described. The equivalence principle says that the physics at the horizon for a freely falling observer should look like the physics of flat space-time. No walls, no barriers, no drama. The AMPS argument shows that these three principles are contradictory. Here is the sketch of why. By unitarity, the Hawking radiation must be in a pure quantum state after the black hole has evaporated past the page time. This means the late Hawking radiation must be entangled with the early Hawking radiation, which is the only system available to provide the purification. But by quantum field theory near the horizon, the late Hawking radiation must also be entangled with the interior of the black hole, because quantum field theory requires that the vacuum state near the horizon is entangled across the horizon in a specific way. A particle just outside the horizon must be entangled with its partner just inside. This double entanglement with both the early radiation and the interior is forbidden by quantum mechanics. A particle cannot be maximally entangled with two different systems simultaneously. This is the monogamy of entanglement. The only way out within the AMPS framework is to cut the entanglement between the late radiation and the interior. But if the entanglement across the horizon is cut, the vacuum state near the horizon is not the standard vacuum state. It is an excited state. It contains high energy quanta. An infalling observer would encounter these high energy quanta at the horizon, a firewall. The no drama condition is violated, so either unitarity fails, or effective field theory outside the horizon fails, or the infalling observer hits a firewall. One of the three principles has to go, and all three seem foundational. Most physicists believed that quantum mechanics was right, and that the resolution would involve some modification of the general relativistic picture of the interior of a black hole. But the specific nature of the modification remained unclear. And this is where the 2019 result comes in. In 2019, the papers that would become known as the island formula papers were published. The key papers were by Almheiri, Engelhardt, Donald Marolf, and Henry Maxfield, known as AEMM, and by Geoffrey Penington. The papers derived what is called the island formula, and what it implies is exactly what the title of this video describes. Information does come out of a black hole, and it does so through a mechanism that, while not violating relativity in the conventional sense, is so strange that it fundamentally changes our understanding of the interior of the black hole and of the nature of space-time. Let me describe what the island formula says and how it works, because the idea is both beautiful and genuinely surprising. I will need to introduce some concepts from quantum information theory to do it justice, but I think the effort is worth it. The key concept is quantum entanglement entropy. In quantum mechanics, two systems can be entangled, meaning their quantum states are correlated in ways that have no classical analog. If system A and system B are entangled, a measurement on A instantaneously affects what we can predict about B regardless of their separation. I discussed this in detail in the video about Bell's theorem and quantum reality. The entanglement entropy of a region is a measure of how entangled that region is with the rest of the universe. A region that is not entangled with anything has zero entanglement entropy. A region that is maximally entangled with its complement has an entanglement entropy equal to the logarithm of the dimension of its Hilbert space. Now consider the Hawking radiation emitted by an evaporating black hole. As the black hole emits radiation, the radiation and the black hole become entangled. Early radiation quanta are entangled with the remaining black hole. As more radiation is emitted, the entanglement structure evolves. The entanglement entropy of the radiation increases as the black hole emits more quanta, because each quantum carries off some entanglement with the interior. If information is not preserved, the entanglement entropy of the radiation would continue to increase until the black hole has evaporated, at which point the entropy would be at its maximum. The radiation would be maximally mixed, meaning maximally uncertain, containing no information about what fell in. This is what Hawking's calculation suggested. If information is preserved, the situation is different. The entanglement entropy should first increase as the early radiation is emitted and becomes entangled with the interior, but then decrease as the black hole nears the end of its evaporation and the information starts to come out. This specific prediction for how the entanglement entropy should evolve with time is called the Page curve, named after the physicist Don Page, who predicted it in 1993 based on arguments from unitarity without knowing the specific mechanism. The question was, can the entanglement entropy of the Hawking radiation be calculated directly from a first principles quantum gravity calculation? And if so, does it follow the Page curve? This is what the 2019 papers achieved. They computed the entanglement entropy of the Hawking radiation using a specific formula from quantum gravity, the quantum extremal surface formula that had been developed in earlier work. And they found that the result did follow the Page curve. The entanglement entropy of the radiation first increases and then decreases, exactly as unitarity requires. In 2019, the papers that would become known as the island formula papers were published. The key papers were by Almheiri, Engelhardt, Donald Marolf, and Henry Maxfield, known as AEMM, and by Geoffrey Penington. The papers derived what is called the island formula, and what it implies is exactly what the title of this video describes. Information does come out of a black hole, and it does so through a mechanism that, while not violating relativity in the conventional sense, is so strange that it fundamentally changes our understanding of the interior of the black hole and of the nature of space-time. Before I describe what the island formula says, I want to give you the context for why this was possible in 2019 and not earlier. The key mathematical tool that the island formula uses is the quantum extremal surface formula developed by Engelhardt and Wall in 2014. This formula generalizes an older result, the Ryu-Takanagi formula from 2006, which gave a prescription for computing the entanglement entropy of a region in the boundary theory of AdCFT using the area of a specific minimal surface in the bulk gravitational theory. The Ryu-Takanagi formula had been extraordinarily successful. It made precise and testable predictions about entanglement entropy in strongly coupled quantum systems using gravitational calculations. And its predictions were confirmed in many independent ways. It was clear that the formula captured something deep about the relationship between entanglement and geometry. The quantum extremal surface formula extended this by including quantum corrections, allowing for the possibility that the relevant surface was not just the classical minimal surface, but included a quantum contribution from the entropy of bulk matter fields. The island formula takes the quantum extremal surface formula and applies it to the specific problem of computing the entanglement entropy of the Hawking radiation. The prescription is compute the entropy of the radiation region, but include in the computation not just the radiation itself, but also any island regions that minimize the total quantum extremal surface formula. An island is a region of space-time that, when included in the calculation, reduces the total entropy below what it would be without the island. For a black hole in an early stage of evaporation, the dominant contribution to the entropy calculation comes from the radiation region alone, with no island. The entanglement entropy of the radiation increases as the black hole emits more radiation, consistent with Hawking's calculation. But for a black hole past the page time, the calculation finds that including an island, a region inside the event horizon, gives a lower total entropy than the calculation without the island. By the quantum extremal surface prescription, the physically correct answer includes the island. And when the island is included, the entanglement entropy of the radiation follows the page curve. It increases, reaches a maximum, and then decreases as the black hole continues to evaporate. This is the resolution of the black hole information paradox. The entanglement entropy follows the page curve, unitarity is preserved, information is not lost. But here's the part that is most extraordinary. To get this result, the calculation had to include something that it initially seems like it should not include. It had to include a region inside the black hole. The island is a region of space-time inside the event horizon. It is, in the naive sense, behind the point of no return. Nothing can travel from the island to the outside. And yet, in the quantum gravity calculation, the island must be included in the description of the Hawking radiation in order for the entanglement entropy to follow the page curve. What does it mean for a region inside the black hole to be part of the quantum system that describes the radiation outside the black hole? This is the question that has been driving theoretical physics ever since the 2019 papers. The answer, still being worked out, has profound implications for the nature of space-time itself. The most natural interpretation, which has been developed by many researchers in the years since 2019, is that the island is not causally disconnected from the exterior in the way the classical space-time picture suggests. There is a quantum mechanical connection through entanglement between the island region and the exterior Hawking radiation. This connection is not a traversable wormhole in the classical sense. Information cannot travel through it at will, but it is a real quantum correlation, a real entanglement between the interior and the exterior that has physical consequences for the entropy of the radiation. The specific mechanism was suggested in a remarkable and highly technical paper by Juan Maldacena and Xiaoyang Qi. They showed, in a specific model of quantum gravity called the SYK model, that when two entangled black holes are connected by a specific quantum circuit, a wormhole forms between them. The wormhole is not a shortcut for conventional travel. An object falling into one black hole would not emerge from the other, but quantum information can be transmitted through the wormhole in a specific way that allows the entanglement entropy of the Hawking radiation to follow the Page curve. The interior of the black hole, the island, is connected to the exterior radiation through this quantum wormhole, this entanglement-based connection that has no analog in classical physics. This is the sense in which something is coming out of a black hole, not matter, not radiation in the conventional sense. Quantum information transmitted through entanglement, through a connection that is real but that has no classical analog, from the island inside the black hole to the Hawking radiation outside. I want to be careful about what this does and does not imply. This does not mean that you could jump into a black hole and have information about you emerge on the other side. The transmission of information through the quantum connection requires a very specific protocol called the Preskill protocol that involves quantum operations on the entire Hawking radiation field and on a reference system outside the black hole. This is not an operation that any realistic observer could perform. The black hole is an exponentially complex quantum scrambler. It takes the information you put in and scrambles it across the Hawking radiation in a way that requires exponential quantum computational resources to decode. The information is there in principle, but it is practically inaccessible. What it does imply is that the event horizon is not the one-way membrane that classical physics describes. At the quantum level, there are correlations, entanglement connections between the interior and the exterior that carry information. The interior of the black hole is not causally disconnected from the exterior in the full quantum mechanical picture. It is entangled with it, and that entanglement is what allows the information to be preserved. Now, let me take you to what I think is the deepest implication of the island formula and the quantum extremal surface, which is not about information preservation per se, but about the nature of space-time itself, because the 2019 results do not just tell us that information is preserved. They tell us something profound about where the interior of the black hole actually is in the quantum mechanical description. In the classical picture of a black hole, the interior is a distinct region of space-time causally disconnected from the exterior by the event horizon. The space-time inside the horizon is as real as the space-time outside. Things exist inside the black hole. The singularity at the center is a real feature of the space-time geometry. The region between the horizon and the singularity has a definite structure, described by the Schwarzschild or Kerr metric. But the quantum picture that the island formula suggests is different. The interior region, the island, is not a separate place. It is part of the quantum description of the exterior Hawking radiation. The interior and the exterior are not two separate regions connected by a horizon. They are two descriptions of the same quantum system related by the complex quantum entanglement structure that the island formula describes. This is connected to a broader idea in quantum gravity that has been developing for years, sometimes called the ER equals EPR conjecture, proposed by Maldacena and Susskind in 2013. ER stands for Einstein-Rosen, the name for a wormhole connecting two regions of space-time, which was first described by Einstein and Rosen in 1935. EPR stands for Einstein, Podolsky, and Rosen, the names attached to the quantum entanglement scenario that I discussed in the Bell theorem video. The conjecture says that ER equals EPR any two entangled quantum systems are connected by a wormhole, and any wormhole connects two entangled quantum systems. Entanglement and wormholes are not different things. They are the same thing described in different languages. The historical irony here is extraordinary. In 1935, Einstein wrote two papers. In one, with Podolsky and Rosen, he described quantum entanglement and argued that it showed quantum mechanics was incomplete because it seemed to require instantaneous action at a distance. In the other, with Rosen, he described what we now call wormholes, solutions to the Einstein field equations that connect two distant regions of space-time through a tunnel. Einstein considered both of these to be problematic features of their respective theories, indications that the theories were incomplete. He never imagined that they might be the same thing. The ER equals EPR conjecture says they are. The entanglement that Einstein worried about in the EPR paper is the same phenomenon as the geometric connection that Einstein described in the Einstein-Rosen paper. Entanglement creates geometry. Quantum correlations between distant systems are, in the appropriate description, space-time connections between those systems. When two particles are entangled, they are connected by a Planck scale wormhole. When two black holes are entangled, they are connected by a macroscopic wormhole. If ER equals EPR is correct, it means that space-time connectivity, the fact that different regions of space are connected, emerges from quantum entanglement. When two quantum systems are entangled, there is a wormhole connecting them. When they are not entangled, there is no wormhole, meaning there is no space-time connection in the quantum gravity sense. The geometry of space, the topology of space-time, which regions are connected to which other regions, is determined by the pattern of quantum entanglement. This is a radical claim. It says that space is not fundamental. It is not the primordial stuff of reality. It is a derived quantity, an emergent feature of the quantum information structure of the universe. The connectivity that we call space, the fact that there is a path between 2 points, is a consequence of the quantum entanglement between the degrees of freedom at those points. Space-time geometry is quantum information geometry. This picture, which is still very much a work in progress and which has not been fully developed into a complete and consistent theory, connects to the holographic principle and to the ADS-CFT correspondence. In the ADS-CFT framework, the spatial structure of the bulk gravitational theory, including the interior of black holes, is encoded in the entanglement structure of the boundary quantum theory. When we compute the entanglement entropy of a region of the boundary, we are computing the area of a surface in the bulk. The Ryu-Takayanagi formula, which gives a precise relation between boundary entanglement entropy and bulk geometry, is the specific mathematical expression of this connection. The island formula is a generalization of the Ryu-Takayanagi formula to situations involving black holes and quantum corrections. When a black hole is present, the formula must include contributions from quantum corrections to the geometry, and these quantum corrections are what lead to the island. The island is not a separate region of space-time that exists independently. It is a feature of the quantum geometry of the bulk, a region whose contribution to the entanglement entropy becomes significant when the black hole has evaporated past a certain point. What this means physically is that the interior of the black hole is not fully autonomous. It is not a completely separate place, disconnected from the exterior. At the quantum level, the geometry of the interior is determined by and is equivalent to certain features of the quantum state of the exterior radiation. The interior is not behind an impenetrable barrier. It is connected to the exterior through the quantum entanglement structure that is, in the ER equals EPR picture, the same thing as the space-time connection we call the horizon. I want to say something about the current status of these ideas, because I think honest representation of the state of the science is important. The island formula has been derived rigorously in specific models, particularly in two-dimensional dilaton gravity models that can be solved exactly. These models are simplified versions of gravity in lower dimensions, and it is not guaranteed that every feature of the two-dimensional results extends to four-dimensional gravity. The derivation has also been carried out in the JT gravity model and in the CGHS model, and the results are consistent. But four-dimensional black holes, the kind that exist in nature, are more complicated, and the full derivation has not been completed in that context. The ER equals EPR conjecture is more speculative. It is supported by consistency arguments and by specific examples in the ADS CFT framework, but it has not been proven in the general case, and it remains controversial. Some researchers find it compelling as a guiding principle. Others are skeptical of its general validity. The specific claim that any pair of entangled particles is connected by a Planck scale wormhole is difficult to test directly and has not been confirmed experimentally. What I can say with confidence is that the island formula resolves the black hole information paradox, at least in the models where it can be derived rigorously. The entanglement entropy of the Hawking radiation follows the Page curve. Information is preserved. The black hole information paradox, which seemed for 40 years to require a fundamental modification of quantum mechanics, has been resolved without modifying quantum mechanics by developing a better understanding of the quantum geometry of space-time near and inside the black hole. And I can say that the resolution points toward a picture of space-time that is more deeply informational than we previously understood. Space-time is not just a background within which quantum systems evolve. Space-time connectivity, the very structure of space, is a feature of the quantum entanglement structure of the physical degrees of freedom. The interior of a black hole is connected to the exterior not by classical geometry, but by quantum entanglement. The horizon is not an impenetrable barrier in the quantum mechanical picture, but a surface across which entanglement connects the inside to the outside in ways that preserve information. Now let me connect this to the broader picture that I have been developing across this series of videos, because I think the black hole information paradox and its resolution are in a certain sense the most profound test case for the information picture of physics that I described in the previous video. If information is fundamental, if the universe is made of information, if the quantum state of the universe evolves unitarily and never destroys information, then black holes must not destroy information either. The island formula confirms this. Black holes do not destroy information. They scramble it, encode it in the Hawking radiation in an exponentially complex way, and eventually return it to the exterior universe. The information about everything that has ever fallen into a black hole, every star, every planet, every organism, every thought recorded on any medium that fell in, is encoded somewhere in the Hawking radiation, inaccessible in practice, present in principle. And this means that the black hole is not the cosmic information destroyer that it seemed to be for 40 years. It is the cosmic information scrambler, the most extreme information scrambler in the universe, taking organized, structured information and converting it into featureless seeming thermal radiation in a way that is practically irreversible but quantum mechanically reversible. The information is not gone. It is just in the hardest possible form to decode. There is a specific result by Patrick Hayden and John Preskill published in 2007 that is relevant here and that I find both remarkable and somewhat playful. They showed that if an observer outside the black hole has access to the complete Hawking radiation emitted by the black hole up to some point, and if an additional small piece of information is then thrown into the black hole, the information about that additional piece is encoded in the subsequent Hawking radiation almost immediately after a time that scales logarithmically with the size of the black hole rather than with the much longer evaporation time. The black hole encodes and returns information quickly, not slowly. It is a fast scrambler, and it returns information to the outside universe much sooner than naively expected. This result, combined with the island formula, gives a fairly complete picture of information flow in and around a black hole. Information falls in. The black hole scrambles it across the Hawking radiation in a way that is quantum mechanically unitary. The information is encoded in the correlations between early and late Hawking radiation. As the black hole evaporates, more and more of the information becomes accessible to an observer who has collected all the radiation from the beginning. By the end of the evaporation, all the information has been returned to the outside universe, encoded in the totality of the Hawking radiation. But there is one more piece of the story that I want to describe, because it connects the information paradox to the firewall paradox in a way that illuminates what the island formula means for the interior of the black hole. Remember that the AMP's firewall paradox said that you cannot simultaneously have information preservation and a smooth horizon for an infalling observer. If the Hawking radiation is entangled with the interior in the way required for information preservation, then there is a firewall at the horizon that would destroy any infalling observer. The island formula resolves this by changing what we mean by the interior. In the island picture, the interior of the black hole that is relevant for the quantum computation, the island, is not the same thing as the classical interior that an infalling observer would experience. The classical interior, the region that the infalling observer falls through when they cross the horizon, may indeed be smooth and well behaved, consistent with the equivalence principle. The quantum interior, the island that must be included in the entropy calculation, is a different thing. A region that is defined not by classical geometry, but by quantum extremal surfaces. This distinction between the classical interior and the quantum interior is subtle and is still being worked out by researchers. But the broad picture that is emerging is that the geometry of the black hole interior is more complex in the quantum description than in the classical description, that there is a sense in which the interior exists and a sense in which it is part of the exterior, and that these two senses are compatible because the quantum entanglement structure of the black hole is more sophisticated than classical intuition suggests. I find this picture deeply fascinating because it suggests that our classical intuition about the interior of a black hole, the intuition that says there is a definite region behind the horizon that is causally disconnected from the exterior, is an approximation that breaks down at the quantum level the classical description of space-time geometry as a fixed background within which quantum systems evolve, is inadequate when the quantum state of the system is sufficiently complex. When the black hole has evaporated past the page time, when the quantum entanglement between the interior and the exterior has reached a certain level, the classical geometric description of the interior becomes unreliable. The island formula provides the quantum correction, and the quantum correction is that the interior is, in a specific technical sense, part of the exterior. This is not paradoxical or inconsistent. It is what quantum gravity looks like when you take it seriously. Space-time is not fundamental. It is an emergent description that is valid in certain regimes and breaks down in others. The breakdown happens specifically in regions of high entanglement entropy, in regions where the quantum information structure of the system is sufficiently complex to dominate over the classical geometric structure. Black holes are exactly such regions, which is why they have been the testing ground for these ideas. The result from 2019, the island formula, the quantum extremal surface, the information coming out of the black hole, is the most direct evidence we currently have that space-time is not fundamental, that gravity is not fundamental, that the geometric structure of reality is a description, an approximation, an emergent pattern in a more fundamental quantum informational substrate, and that the information in the universe, including the information about everything that has ever fallen into a black hole, is preserved by the most fundamental laws of physics, laws that operate not at the level of space-time geometry, but at the level of quantum information. The result from 2019, the island formula, the quantum extremal surface, the information coming out of the black hole, is the most direct evidence we currently have that space-time is not fundamental. That gravity is not fundamental. That the geometric structure of reality is a description, an approximation, an emergent pattern in a more fundamental quantum informational substrate. And that the information in the universe, including the information about everything that has ever fallen into a black hole, is preserved by the most fundamental laws of physics, laws that operate not at the level of space-time geometry, but at the level of quantum information. Let me try to make this concrete by thinking through what it means for a specific situation. Imagine a star with all its planets and all the life that might have evolved on those planets that falls into a black hole. All that information, the specific arrangement of every molecule in every organism on every planet, the history encoded in the DNA of every species, the physical record of every event that occurred in that solar system, all of it crosses the horizon and disappears from the perspective of the outside universe. For a time, from the outside, it is simply gone. The black hole's external properties, its mass, its charge, its angular momentum, give no hint of the specific contents it has absorbed. Two black holes of the same mass, one formed from that star with its planets and life, and one formed from an equal mass of hydrogen gas, look identical from the outside. But as the black hole evaporates, the information does not stay gone. It is being encoded through the island mechanism in the quantum correlations of the Hawking radiation. Early photons of Hawking radiation are becoming entangled with later ones in specific patterns that reflect the specific quantum state of the infalling matter. The encoding is extraordinarily complex, practically irreversible. But the information is there in the correlations being gradually transmitted from the island inside the black hole to the radiation outside. The organisms that lived on those planets, their molecular configurations, their evolutionary history, the specific pattern of every neural firing in every brain, all of it is being encoded in the correlations between photons emitted over the course of the black hole's evaporation. By the time the black hole has fully evaporated, all of that information has been returned to the outside universe, scrambled beyond any conceivable reconstruction, but present. This is what I mean when I say the universe keeps its books perfectly. Nothing is truly lost. The most extreme information scrambler in the universe, the black hole, does not destroy information. It transforms it, redistributes it, encodes it in the thermal radiation in a way that makes it exponentially difficult to recover. But the laws of quantum mechanics ensure that it is recoverable in principle because those laws require unitarity, and unitarity means nothing is truly lost. You ask what could come out of a black hole. Information comes out, but quantum mechanically, through the entanglement structure of the Hawking radiation, through the island that must be included in the entropy calculation, the information that fell in does not stay in, it returns. Encoded in the thermal radiation that the black hole emits over its lifetime, structured in the quantum correlations between photons emitted at different times, impossible to decode without access to the entire evaporation history and quantum computational resources beyond anything imaginable. But there, the universe keeps its books perfectly. Everything that falls into a black hole is eventually returned in the most scrambled and inaccessible form imaginable to the outside universe. The ledger of information is balanced. The second law of thermodynamics increases entropy going forward. But quantum mechanics ensures that the information is never lost. The two laws are consistent because entropy is a measure of missing information, not of destroyed information. The information is always there, somewhere, in the quantum state of the universe. Even inside, and eventually outside a black hole. The universe keeps its books perfectly. Everything that falls into a black hole is eventually returned in the most scrambled and inaccessible form imaginable to the outside universe. The ledger of information is balanced. The second law of thermodynamics increases entropy going forward, but quantum mechanics ensures that the information is never lost. The two laws are consistent because entropy is a measure of missing information, not of destroyed information. The information is always there, somewhere, in the quantum state of the universe, even inside and eventually outside a black hole. I want to close with a reflection on what the island formula and the larger program of quantum gravity it represents actually tell us about the nature of physical reality, because I think the implications go deeper than the resolution of a specific paradox, important as that is. The classical picture of a black hole is one of the most dramatic in all of physics, a region of space-time from which nothing can escape. An event horizon that is a one-way membrane, an interior that is causally disconnected from the rest of the universe. An infalling observer who crosses the horizon and is forever cut off from the outside, free to send signals into the interior but unable to receive any from outside. This picture is vivid, precise, and grounded in the mathematics of general relativity. The quantum gravity picture that the island formula provides is more subtle and in some ways more strange. The interior of the black hole is not a separate place in the full quantum mechanical description. It is connected to the exterior through quantum entanglement. The horizon is not a one-way membrane in the quantum picture. It is a surface across which entanglement connects the inside and the outside, allowing information to be transmitted through quantum correlations that have no classical analog. The event horizon, the most dramatic feature of the classical black hole, is less dramatic in the quantum picture. It is a location where the quantum entanglement structure changes, where the island becomes relevant, where the geometry of the quantum extremal surface shifts, but it is not an impenetrable barrier. This shift from the classical to the quantum picture reflects a deeper change in how we understand spacetime. In the classical picture, spacetime is fundamental. It is the arena within which physics happens. The geometry of spacetime determines the paths of particles and the propagation of fields. The event horizon is a geometric feature of spacetime, a boundary defined by the causal structure of the geometry. In the quantum gravity picture, spacetime is not fundamental. It is emergent. The geometry of spacetime is a derived quantity, an approximate classical description that arises from the quantum information structure of the underlying degrees of freedom. The event horizon is not a fundamental feature of reality. It is a feature of the classical approximation that becomes inaccurate in the quantum regime. When the entanglement entropy of the black hole has grown large enough that the island prescription changes the calculation, this emergence of spacetime from quantum information is one of the most profound and active research directions in theoretical physics. The specific mechanisms are still being worked out. The general picture, geometry from entanglement, spacetime from quantum information, is supported by a growing body of evidence from ADS divided by CFT, from the island formula, from the ER equals EPR conjecture, and from the general consistency of the quantum extremal surface calculations. What it means at the most fundamental level is that the fabric of space-time that you inhabit, the space around you, and the time through which you move is not the most basic thing. It is an emergent description of something more fundamental, something quantum mechanical and informational that lies beneath the geometry. The space-time that general relativity describes is an approximation valid at the scales and energies of everyday experience that breaks down at the Planck scale and in the extreme environments of black holes. You are embedded in a space-time that is itself made of information. The space between you and the nearest star is a quantum informational structure, an entanglement pattern between the quantum degrees of freedom that fill the vacuum. The time through which you move is an emergent property of that entanglement structure. The gravity that keeps you on the Earth is the curvature of an emergent geometric description of quantum entanglement. And the black hole information paradox, the paradox that seemed for 40 years to require a modification of quantum mechanics, is resolved not by modifying quantum mechanics, but by recognizing that space-time, including the interior of the black hole, is not fundamental. The information does not stay inside the black hole because the inside is not truly separate from the outside. The quantum entanglement connects them. The island is real, and the information comes out, not quickly, not in any form that can be practically decoded, not through any mechanism that a classical observer could exploit to escape the black hole or receive messages from within it, but quantum mechanically, through the entanglement structure of the Hawking radiation, through the island that must be included in the entropy calculation. The information that fell in does not stay in, it returns. Encoded in the thermal radiation that the black hole emits over its lifetime, structured in the quantum correlations between photons emitted at different times, impossible to decode without access to the entire evaporation history and quantum computational resources beyond anything imaginable. But there, the most impossible thing in physics is happening. And it is happening because information and the quantum mechanics that governs it is more fundamental than the space-time geometry that seemed to imprison it. If this changed how you think about what a black hole actually is, if the interior looks different to you now, knowing that it is connected to the exterior through quantum entanglement in ways that preserve information, tell me in the comments. Tell me whether you find the firewall paradox more or less disturbing after the island formula. Tell me whether ER equals EPR seems to you like a profound insight or like speculation that has run ahead of the evidence. These are the questions at the frontier of quantum gravity, and they are the ones that physics is actively working to answer. And subscribe if you want to stay at the frontier where the deepest physics meets the most fundamental questions about the nature of space-time, because this story is far from over.